I need you to discuss with me the plan for today. Okay, so some of the topics we have done, but when I wrote everything on the projector, it seems a bit busy. So the first one that we agreed on was multi-phase, free surface, Lagrangian, and liquid film. You still want to do that? Okay. After that, I still owe you to show you how to run it in parallel, do the domain decomposition and reconstruction. And also, I would like to do a little exercise in doing a three-dimensional simulation with free surface flow solver. The third one that we agreed was to discuss discretization best practice. And for that one, I would like you to try something hands-on, which is to take one of the tutorials from the original settings to the settings that I recommend and see what happens. Then we have several things. Programming, that has not been discussed yesterday at all. Do we have to do programming? I thought so. Okay. And the one that was on the list from yesterday was meshing. Okay, so what about meshing? Do we have to do that too? Well, that's too many.
Is Snappy Hex maker?
Good.
You were saying?
Is it Snappy Hex mesh then?
Yeah. Anyone using Snappy? You know how to use it?
More or less.
So what's the big deal? Okay. There is too much lecturing for me and not enough exercise. So we'll have to do something with the programming. Who has done any programming in OpenFOAM before? Do you know what you're doing, or you're just doing monkey see, monkey do and hoping for the best? Okay, there is a bit of that. Okay. So I suggest that we do 1 and 2, then do some programming, move discretization best practice in the afternoon, and then discuss between open panel and meshing. Okay? Okay. So multi-phase and free surface flows are getting more and more important in CFD today. We have been doing for quite a long time, and the problem is that there is no one way of doing multi-phase and free surface flow. So what I'm going to do in these slides is review some concepts of multi-phase modeling with different level of approximation, including Eulerian multi-phase flow, also called Euler-Euler, Euler-Lagrange modeling, where the dispersed phase is modeled by Lagrangian particles being tracked through the mesh, and a specific case, the volume of fluid model, which basically takes into account two fluids with a discrete surface in between. We will also mention something about the thin liquid film and free surface tracking, because in naval hydrodynamics, that one seems to be more and more interesting. Okay? So the part of the story that you all know is the idea of a single phase flow. Okay? So we have a continuum with continuous properties, which are density, viscosity, equation of state, etc. And then we can write out the equations for conservation of mass, conservation of momentum, and conservation of energy. And this is a standard solution algorithm that we will play. Okay? When we talk about multi-phase flows, there is so many different things that we can account for. Okay? So my favorite example will be a bottle of Coca-Cola. For the drinkers, the bottle of beer. Okay? Where you have a mixture between the liquid phase and the gas phase, and you can consider that one of them to be the background phase, for example, the beer. Okay? And then the bubbles within the beer will be the dispersed phase. Okay? One of the ways that this is modeled is by using a volume fraction approach, where you assume that there are two interpenetrating continua basically on top of each other, and then you introduce a variable like volume fraction, which tells you what percentage of a certain material there is within a volume that you will then squeeze towards zero. Okay? Of course, there are fundamental problems about that, because if you squeeze the volume too much, you will end up either in the liquid or in the gas, and that is not the point of the equation. Now, if you think about the volume fraction in a bottle of Coca-Cola, do you have any idea of what would be the percentage of air volume in a bottle? 0.1%? 1, 10, 50, 100%? Well, when you finish the Coca-Cola, then it's 100%, right? Okay. But when you look at the flow that has got discrete bubbles going on in the background phase, a typical volume fraction will be 1, 2, 3%. And if you have a volume fraction which is much higher than that, this no longer looks like a background phase with the bubbles. Okay? In the extreme case, you can have a glass of water sitting on the table, where at the bottom of the glass you have the liquid, and above the liquid you have the air, meaning that you have full separation between the phases. Okay? So the Euler-Euler approach that I'm talking about have this idea of interpenetrating continua. However, the amount of volume fraction that you have is still relatively low. Okay? Another example, when it's raining, what is the volume fraction of liquid in the air? Well below 1%. Okay? The mass fraction will be higher because of the density ratio, but the volume fraction is very low. Okay? If the volume fraction is extremely low, you can represent the dispersed phase, meaning my droplets, as Lagrangian particles that run through the mesh and interact with the background mesh. So let's just have a quick look at this idea of a coupled approach between the two phases. So what happens when you have a background air and droplets of rain falling through it? Okay, first you're going to have the conservation of mass for the air. You're going to have the conservation of mass for the water. You're going to have conservation of momentum for air and water, where they will exchange momentum between the two. What does that mean? It means as the droplet is flying through the air, it will feel the drag law, which will slow it down, okay? And because of the motion of the droplet will cause the flow within the fluid, meaning it will generate fluid momentum because of the other half of the drag terms, okay? The third thing that I need to have is the volumetric continuity equation, because when I imagine one phase plus the other phase, I need to get the complete continuum, and there is the conservation, if you like, of volume for the background phase. And the fourth thing that I need to know is something about the distribution of phases. Where are these air droplets? Okay? So in the Eulerian approach, we do that by taking a look at the set of equations that are working and introducing a concept called the volume fraction. Okay? Now, as I said, the volume fraction is a bit difficult because if the droplet is small enough and I squeeze my point beyond the size of the droplet, I'm going to end up either in liquid or in the air. But I can introduce the concept of probability of a droplet being present at the same location, which is basically the same story. It says within this volume there is 3% of liquid and 97% of air. When we derive the equations for it, we will use something called the conditional averaging technique from Dopazzo, and it will have a set of equations that looks as follows. Okay. First, the phase continuity equation, where alpha, you can take a look at the probability of the droplet being present, or the volumetric fraction of air within the volume. Okay? The transport equation says d alpha dt plus div u alpha equals 0. And what is important is that alpha gets carried by the velocity of alpha. The second thing that I have is the phase momentum equation, div alpha u by dt, convection term, diffusion term, pressure gradient, gravity, and momentum exchange between the two phases. However, I can imagine myself a variable which is equal to the velocity of the air if I'm in the air and equal to the velocity of the water. So based on that, I will assemble the velocity for the sum of the phases as sum of alpha I ui, and the continuity equation for that same velocity basically says div u equals 0. Now, this can be further complicated if we have compressibility in either of those phases, but that gets too complex for me at the moment. Okay? So, apart from the stuff that we are used to, we will now have one additional equation which will follow the presence of a certain phase. Okay. The important part in the game, in the first principle, is the momentum exchange terms. Okay? And if I tell you there is a liquid droplet going through the air, can you tell me how much momentum it will exchange with the continuous phase? Yes, of course you can. 1/2 rho minus rho air times u squared. Okay? So this is a drag law. I'm missing a CD. And the CD will be the drag coefficient, which depends on the shape and size of the droplet. Do you know anything about the shape and the size of the droplet? Well, if it's small enough, I can assume that it is spherical. But in order for this model to work, you need to tell me what is the size of the droplet in the rain or the size of the bubble in Coca-Cola, which is not an easy game. However, if we wish to model the momentum in this simple manner, you have to assume that your droplets are something called monodispersed, meaning there is only one size of droplets present everywhere. Okay? If you have a realistic situation where there are several droplet sizes present at the same time, then my volumetric equation is no longer enough, but I have to have a description of the distribution of droplet sizes, plus I need to have some terms called breakup and coalescence terms, which tells me what happens when two droplets are close to each other or when the big droplets break up into the second one. Okay? There are several ways of describing this distribution, either by introducing several droplet sizes for different classes of droplets, or by introducing something called QMOM or DQMOM, which is a way of describing a droplet distribution in a different manner. When you solve equations like this, we face one big problem, and that is my alpha equation. Okay? So the issue is that each of the velocities is being carried by its own phase velocity. However, the continuity equation that we solve, which is the pressure equation, needs to be the same for all. In other terms, I can get you the velocity for the continuum, which is that one, but I don't know how to split it into phase velocities, because if I interpolate alpha onto the phase, there is no guarantee that the phase velocity equation will be satisfied. Okay? So in the PhD thesis at Hrojve, which is the basis of the system, there is a reformulation of the alpha equation, which basically says something like this, and now we have the transport in convection with the continuum velocity, and then we have one additional term here, which is div u alpha minus u beta, alpha times 1 minus alpha, which takes into account the distribution between the two phases. Okay? You will see that this is implemented in all multi-phase models in foam, and it seems to work quite well, so it is applied across a region of conditions. Now, the solvers can be very simple. The simple solver is called bubble foam, or can be more and more complex depending on how much further physics you hook up to the system. For example, multi-phase Euler foam, which will be able to deal with things like fluidized bed simulation and other more complex problems. Okay? Please be careful. As the model gets more and more complicated, the basic physics of two momentum equations, one continuity equation, single pressure, and n alpha equations gets more and more convoluted and more difficult to handle. Okay. An example? So the simulation that I'm showing you here is something called the bubble column, where we have the liquid up to the free surface here, and we have an incoming stream of bubbles which will race through the system. And because the bubbles are raising, you can see how the flow of bubbles creates this column of raising air through the liquid, but it also introduces quite a lot of flow into the liquid phase itself. Note, up here I have a free surface, meaning that above the free surface there is only air, and the system can quite happily handle this combination of the free surface flow and the bubbles. Okay? The solvers for monodispersed system, meaning there is one size of bubbles, are quite well established and they work quite well. As it gets more and more complicated, we have several implementations, either of the method of classes or of the DQ-MOM method, but they are not as easy to handle as these. Okay. The special case of the VOF system that we have here is the idea of free surface flow. Now, what is going on here is that the two equations that represent the momentum are now never present in the same place. Okay? So you have the free surface. Below the free surface there is water. Above the free surface there is air. And if you remember, the momentum equations that I had before used to have alphas in here. But now, alpha is either 1 or 0. So rather than having two velocity fields and drag terms with them, I can collapse the two equations on top of each other and create one single continuum momentum equation. Okay? This is what we call a free surface flow assumption, because you never allow both liquids to be present at the same time. Now, the traditional derivation still follows the same way. So I have my volume fraction variable, which here I called gamma, to make a difference. And in the momentum equation, I now have the pressure gradient term, the stress term, convection, ddt, body force, but instead of the momentum exchange term, I have the surface tension term. Okay? In order for this to work, I have to define sigma and rho as a function of my volume of fluid variable. Okay? So the idea is that I will collapse the two phases on top of each other, which allows me to define a single velocity, single density, and a single kinematic viscosity term by saying gamma u1 plus 1 minus gamma u2, or gamma rho 1 plus 1 minus gamma rho 2, where gamma equals 1 represents fluid 1, and gamma equals 0 represents fluid 0. Okay. Of course, in a numerical solution, my alpha equation will never be a step. Okay? Remember the test that we did with scalar transport form previously? Okay, but this time it worries me a little bit, but not too much. Because we said that my variable gamma, or if you like alpha, represents the fraction of the volume of phase 1 in a cell. Well, it is perfectly possible that the cell is half filled, right? In which case, gamma will be 0.5, and the mean density will be 0.5 times 1000 plus 1 minus 0.5 times 1, which is what, 500 and a half. Okay? That will be the mean density of the cell. Okay? This system works quite well, with the issue that solving an equation d alpha dt plus d mu alpha equals 0 does not account for the fact that the interface needs to remain perfectly sharp. So in order to deal with that, we borrow the term from the previous formulation, which used to say u alpha minus u beta alpha times 1 minus alpha, where u alpha and u beta are velocities of air and water. Okay? Now there are no drag terms. In fact, there is never velocity of air and water possible because I either have water or air. So that term has been artificially introduced in order to make sure that your interface remains sharp. Okay? Previously, of course, the same thing needed to be done, but we used to do that by using compressive numerics, where you have special discretization schemes on this term, and then that term is no longer necessary. Okay? So this basically tells you the VOF formulation that we use, and that term which takes into account the fact that the interface needs to remain sharp. The solver here is InterFOAM. It deals with all of the stuff that I showed you before, and it also allows you to use LES and RANS turbulence models and all the other goodies that come with it. Now, please note, on the free surface, you are going to have a big gradient in the velocity because the lighter phase moves more easily than the heavy phase. However, the turbulence model does not account for the presence of the interface, so kindly be careful when you're using this formulation. Okay. Apart from the terms that I showed you before, we also need to account for surface tension. Okay? So the idea of surface tension is that in the presence of a curved surface, there will be a jump in the pressure from one side into the other. And in order to account for that, you have to calculate the surface curvature. Okay? The surface curvature is calculated by using the gradient of my volume fraction variable. Okay? That will be normal to the surface. When I divide it by a magnitude, this becomes a unit vector, and the divergence of that gradient basically gives me the curvature. Okay? The curvature will of course be present only where the free surface is present. Okay? So if I'm in the liquid or in the air, then grad gamma or grad alpha is 0, and this issue does not arise. And we use something called the distributed form of the surface tension jump, meaning that we will introduce this term across the part of the interface where the interface is smeared. Okay? Again, please notice, unless you're very, very, very lucky, your interface will be smeared. And by very lucky, I mean that your interface coincides with the faces in the mesh and it doesn't move. Okay? And that doesn't make it particularly interesting. Okay. In these formulations, we also use something called the piezometric pressure distribution. Okay? So the idea is this. If you have a glass of water on the table, the distribution of the pressure in the glass will be linear. Okay? Because of the hydrostatic component, which is rho GH. Okay? If the fluid is sitting in the glass, I will simultaneously have a linear distribution of the pressure and the zero velocity, which is not very nice. Okay? Because that means that I have to calculate the pressure one order of accuracy higher than the velocity. And in order to handle that, we decompose the pressure into P equals P rho GH or PD plus rho times GH. Okay? So now my PD remains constant and uniform with uniform zero velocity, and the hydrostatic component can be added to the pressure afterwards. Okay? There is a deeper numerical explanation for this, which basically says that the fluxes need to be staggered with respect to the pressure gradient, and that means that we have moved apart from the hydrostatic contribution from the momentum equation into the pressure equation to get the code to behave properly. Okay? When you need to describe the boundary conditions for my variable P, PD, just assume that you have taken out the Hrojve component. Okay? This solver has been around forever. In fact, it is one of the early solvers written in foam by Dr. Ono Ubin, and we can do all kinds of things with it. Okay, so one of my favorite things is this simulation here, where you take a cylindrical container, I used to say a glass of whiskey, and you spin it round. Okay? When we used to have numerical problems, then the amount of whiskey in the glass would not stay constant, it would slowly disappear, which is clearly a disaster. Okay? So the solver got fixed. So what you can see here is basically a simulation of that kind, but this is not a joke. Okay? In fact, the solver has been used by a manufacturer of laboratory equipment to find out how to optimally shake the container to get the mixing of the chemicals. Okay? The solver has the dynamic mesh features that we'll speak about that maybe some other time. Other simulations of the similar kind will be things like impact of a droplet into a wet wall. Okay? Now here you can see how my free surface breaks up. Any idea why? So the visualization will show the isosurface of volume fraction 0.5. And as long as the thickness of my liquid sheet is big enough to be captured on a mesh, I can see it as a continuous surface. But when the thickness becomes smaller than the mesh size, then the volume fraction disappears. And I can probably show you that better when we take a look at the cut. Okay? Oh, this is not a cut, unfortunately. Okay, but at least you can see what's going on. The early simulations were also targeted to this kind of thing. So what you have here is a 10 micron jet, which is injected into the air. The distance from here to here is slightly below 2 millimeters. And the device that you're seeing simulated here is basically droplet generation for an inkjet. Okay? The droplets here break up because of surface tension. And as you can see, the solver can handle this breakup quite well. There is one further associated effect with this, and that is the effect of the contact angle. Okay? So if the droplet is sitting on the surface, there will be a certain angle between the liquid-air interface hitting the interface of the solid wall, and that is also accounted in the solver by using boundary conditions on the VOF variable at the solid wall. Okay, as I told you, this solver is quite capable of doing all kinds of instability. And yet another example of that is a slightly larger injector of 0.2 millimeter diameters. And the simulation includes the breakup of a fast jet being injected into the quiescent atmosphere at quite a high pressure. And what you can see here is how this free surface of the jet breaks up into droplets in order to get the evaporation. I quite like this movie because first, the mesh is very, very fine, and second, it shows you the limits of what you can do with volume of fluid. Okay? In order for the volume of fluid to work properly, you need to have enough mesh to resolve individual droplets like this. Okay? And when the mesh is no longer fine enough, you're just going to have the volume of fluid void fraction, which is between 0 and 0.5, meaning that you cannot see individual droplets. Okay? They do not disappear. They are present in the simulation because we have strict mass conservation of both phases. However, the modeling of the surface tension and droplet-to-droplet interaction is no longer appropriate. Okay. So, there is a whole set of extensions that have been done with this solver. Over time, you can introduce multiple phases. Each of the phases can have different material properties. You can add the energy equation to the system and or various other features like the dynamic mesh. And here I just included some of the pictures of a device called Tandish, which appears in metallurgy, where you basically pour liquid metal out of a big bathtub, and now I have double interfaces. So my first interface is between liquid metal and slag, and the second interface is between slag and air, where the densities are 8,500 for the liquid metal, about 2,000 for slag, and 1 for air. And the effect that we are looking at is breaking up this protective layer of slag and getting air in direct contact with the metal, plus any issues of slag going out through the exit of the system. Okay? This is a very mature solver. We have done many things with it, and there are really no issues in terms of how the solver operates. When we get to the level where the mesh resolution is no longer sufficiently high to pick up individual droplets, we can switch into the Lagrangian particle tracking model. So the idea of Lagrangian particle tracking is that now we are going to have a single continuum phase, for example air, and into that single continuum phase we are going to inject individual particles which will be solved in a Lagrangian manner, meaning that I solve force equals mass times acceleration, and on the right hand side I can collect as many forces as I like. Okay, so the typical forces that I will introduce are the drag force, the pressure force, virtual mass force, gravity, or any other forces which are relevant for my system. The way the solver operates is that you will take into account the continuum phase as your quote-unquote main Eulerian component, and then as you shoot particles through the mesh, you're going to track them from cell to cell to find out how they interact with the underlying fluid. In order to get the interaction, for example, for the drag force, I need to calculate the relative velocity, meaning that as the particle is tracked through the mesh, it will follow the relative velocity of the particle with respect to the underlying velocity of the fluid, and then you can integrate this motion equation by using, for example, an ordinary differential equation solver. Okay? Furthermore, because the particles are now discrete points in space, we need to make sure that the particle density is reasonable. Okay? An example. Imagine a cell 1 centimeter, 1 centimeter by 1 centimeter, and into it I put a particle which carries 1 liter of water. Okay? This is obviously not physically possible because the volume of that particle is greater than the cell size. Okay? Taking it to the other extreme, you can have 1,000 particles which all carry a smaller mass, but the total volume of the particles is greater than the volume of the mesh. So just like my volume of fluid method, which has got the limit at the lowest volume fraction that I can see, my Lagrangian particle tracking method has got the limit at the highest volume fraction that I can see, meaning that the cells need to be relatively high with respect to the volume fraction that I carry. Okay? Particles. For particle modeling to work well, a reasonable volume fraction is of the order of 1% or less. which is still quite much higher than what you would assume. Okay? In realistic simulations, like for example, internal combustion engine, diesel spray modeling, the number of individual particles is prohibitively large. Okay? So the number of droplets that you're going to have is of the order of 2 billion, and you cannot afford to track 2 billion particles through the system. In order to deal with situations like that, we introduce a concept of a parcel, where my XYZ point does not represent one particle, but a population of particles with the given diameter distribution, with the given mass, surface area, etc., which can then exchange information with the continuum phase. Okay? So in that case, for the drag law, I would know the total mass and the mean diameter, calculate the number of particles, figure out the individual drag law for each of those particles, and then sum it all up. Obviously, the important part of Lagrangian spray will be evaporation. Okay, so evaporation will depend on the difference of the temperature, it will depend on the radius, surface area, etc. And you can exchange mass, momentum, and energy between the continuum phase and the dispersed phase, because, for example, in evaporation, you need to take away the heat from the continuum phase, which means that each of these equations will speak to the others. Okay? Further to that, there is a set of models that involves particle injection. Okay? So how many particles at which rate, at which direction are introduced into the system. Then particle breakup and coalescence. What happens when a parcel A collides with a parcel B? And finally, what happens if a particle or a parcel interacts with the wall? Okay? A good example of that is the diesel spray modeling library, which contains quite a complete set of modeling for internal combustion engines. Again, please be aware, the principle of describing particles is always the same. Parcel modeling is appropriate across a number of different stages. However, the models of breakup, coalescence, primary breakup, momentum exchange, etc., are typically valid for diesel combustion. Okay? So if you want to do something different with your particles, you have to review the models that are implemented and find out whether they're okay for you or not. Okay? An interesting set of applications that we have can deal with the particles at a relatively primitive level. Okay? So forget about population. Just introduce a very large number of particles, chase them through the domain, give them a mean diameter, and if with 4 different mean diameters, you have a very reasonable representation of rate. Okay? On this slide, I can show you, for example, how the exchange of the momentum works between the continuous phase and the particles. So here on the right-hand side, remember what we had in the Euler system? Momentum exchange, okay? Where that momentum exchange in the continuous phase also appeared in the dispersed phase with the opposite sign, because if I'm slowing down the dispersed phase, then I'm accelerating the continuum phase and vice versa. Whereas here, I have the same kind of term, but on the other side, now I have the momentum exchange between the discrete particles. Okay, so the way that's calculated is, as you're following the particles through your domain, you find out the amount of momentum that comes into the cell on that particle and that goes out of the cell on that particle, and the difference remains in the cell. And then you integrate that over all the cells that have, over all the particles that have gone through the cell. Okay? So that will give you this term, 1 over the volume, number of particles in the volume, difference of the momentum plus any other source terms. Okay, so here's a little example of what happens with Lagrangian particles in a domain. So here I want to model what I just described you, which is rain. That will be a bunch of particles here. The flow goes from left to right, and you can see how the injected particles in the domain how they run through the domain and eventually hit the wall. Nowadays, we use this sort of simulations in order to do things like rain hitting buildings or finding out which part of the square will be wet when it is raining, if you have partial canopies and that sort of thing. Okay? Apart from Lagrangian particle tracking, here you also have an effect of what happens when these particles hit the wall. Okay, so let me say a few words about the modeling of such situations. Now, the issue is that this is still a volume of fluid problem. It can be a two-phase problem. I need to deal with it in some way, but there is a very interesting separation of scales. For example, you can have a building whose roof is 100 by 100 meters, but the amount of water that you will get on top of the surface because of rain is less than 1 millimeter thick. Okay? Can I model this by Lagrangian particles? Not really, because it is a continuum film. Okay? So the next option would be modeling it by using a volume of fluid method. But this is also not practical because the size of my domain is 100 meters and the size of the thickness of the film is below a millimeter. Okay? So for those applications, we use something called the liquid film model. Okay? And the idea is that rather than resolving my equations in 3D, I will switch into a two-dimensional representation of the model, which basically takes into account the surface that I am acting on, and at each point of that surface, I will record the height of the film. Okay? So the two working variables that I want to have are the film thickness, meaning h, okay, and the mean film velocity, which will give me the flux of the film going along the surface. There are obviously assumptions. The first assumption is that the normal gradient is 0. The second assumption is that the profile of the velocity is self-similar. But by hooking up these equations, I can come up with an equation set that looks like this. So my first equation is the continuity equation for the film, which says dH by dt, meaning the variation of the film thickness, plus convection is equal to the mass of liquid droplets hitting the film and divided by the area. My momentum equation now looks a bit different than before because I'm solving a two-dimensional approximation of a three-dimensional phenomenon. So the first thing that I have is dHV plus div HVV, which is my convection term, with a correction depending on the shape of the profile. And then I have a set of force terms. Okay, so the first one is tau, friction at the wall, per unit area of the wall. Second, I have the flow above the free surface, which is driving the film. Okay, so if I have a film on my hand and I blow, this act of blowing should be capable of moving the film. The third thing that I have is the gravity, so that the film leaks down. And the fourth and the fifth thing that I have are the gradient of the pressure, which contains 4 parts, and the incoming momentum onto the film. Okay, so what that means is if I have a film like this and a droplet is impacting normal to the film, it will submit the mass and the high pressure which will drive the film away. But if it's hitting it tangential, it will also submit the tangential component of the momentum into the film. The pressure has got 4 components. The first one is the gas pressure. The second one is the normal component of the droplet impact pressure. Okay, so this is the pressure of the droplet hitting it, driving the fluid away. The third component is the capillary pressure, again calculated from surface tension. And the fourth component is my hydrostatic pressure, which will come from the liquid. Okay? Now, there are some further issues. These terms here, oops. These terms here need to account for the fact that my roof surface is not flat. Okay? So if my surface has got an undulation, then there is the equivalent of something called the Christoffel symbols, which take into account the curvature of the space in the calculation. And they are built into the discretization operator for div, grad, and this is this div s and grad s that we have in the part of the code called the finite area method. Okay, so to give you an idea of what this looks like, take a look at this picture. Now, an explanation is required. So here, my simulation is actually 2D, and I'm drawing the free surface by deforming my 2D surface with the height h, which is my variable. Okay? So a little movie. We'll show you the collapse of the blob under surface tension one more time. And if you let it long enough, it will eventually reach the correct shape. The beauty of using OpenFOAM in this sort of technique is that you can combine various approaches to your multi-phase modeling. Okay? So you can start by assuming you have a VOF model, then search for the droplets that are below the size of the mesh resolution, collect the mass out of the VOF model, create Lagrangian droplets, shoot them through the domain. When the droplets come up too close to each other and the volume fraction goes higher than a certain minimum value, say 0.5 or 0.6, you can convert them back into the VOF model and carry all the possible combination. Further to that, you can account for Lagrangian droplets flying through the domain, impacting the wall, and then generating a liquid film, on top of which you can solve not only mass and momentum equation, but also the energy equation, and get effects like, for example, in a diesel spray in an internal combustion engine, when the wall gets wet from the spray, then the spray can evaporate back into the volume. Okay. There is one approach that we did not mention, and that is called the free surface tracking simulation. Okay? So the idea of the free surface tracking simulation will be that I take something like a two-phase flow and say, but I don't care about the flow on the air side. So instead of meshing both the air and the water and then accounting for the presence of interface through surface capturing, meaning the volume of fluid equation of the equivalent, we can basically introduce a single domain where one of the boundaries will be a free surface. Okay? On that boundary, we have a double boundary condition. Okay? So the first part of the boundary condition says that the pressure is fixed. Okay? So pressure at the free surface equals atmospheric pressure. And the second, which says that the surface normal velocity is 0. Okay? Meaning your fluid cannot jump through the free surface. Okay? Now, if you think about the momentum equation, this double boundary condition is not natural because velocity is proportional to the pressure gradient. So if I specify the velocity, that gives me a pressure gradient, not the value of the pressure. Okay? And knowing the value of the pressure at the boundary means that the velocity needs to be calculated because the gradient of the pressure at that boundary is a part of the solution. Okay? So in fact we use exactly this, because when you specify a double boundary condition, you will either get excess velocity or your pressure is not going to match, but based on that you can then calculate the motion of the free surface until you reach the position where the double boundary condition is satisfied. This is what I refer to as surface tracking. Okay? So here's an easy simulation to show you what it looks like. The flow will come from left to right. Here I have a hydrofoil. At the top of the domain, my atmospheric pressure is 0, and I have one incompressible liquid in this game. At the top of the airfoil, the pressure is lower, which will pull the surface down, and that should then create a bunch of waves side to side. Okay, can you see the first wave being created? And that makes the second, then the third, and the fourth wave. Okay? And the solver that I'm using is basically a conventional single-phase flow solver, but apart from the usual stuff, it has got that funny boundary condition which tells me how to deform the boundary at the top. Okay? You can immediately see a problem with it. Okay? And that is that in mesh deformation, you can only go so far. Because if the surface breaks, then you have to do something extreme with the meshing in order to account that for the fact that the topology of your domain has changed. And in fact, even a solver like that has been written. Now, if you think about this kind of formulation, we can take those two solvers side by side and solve it twice. Okay, so here is a simulation of a complex coupling where I have a bubble, which is represented by one domain, the water around the bubble represented by the other domain, and now I have two boundaries like this, but basically sitting on top of each other. Okay? The calculation that I'm going to show you will show you the rising of that bubble in the water. The bubble is of course made out of air, making a lower density, and the difference in the gravity will make it go up. But we will hang our coordinate system onto the bubble to simplify the simulation. So in the first stage, you can see the deformation of the bubble. Okay, take a look at the flow. In fact, inside of the bubble, I also have a double vortex because of the flow of the air, which is driven by the tangential velocity. The bubble did a zigzag, and after a while, it starts going up on a helicoidal trajectory. Okay? So again, this is basically a single-phase solver for a multi-phase flow where the description of the interface is now perfect. Okay? The fact that we have a mesh on the surface of the interface also helps us with the fact that we can calculate the curvature and the surface tension term, which basically gives you a pressure jump from one side into the other. Okay? To complicate things further, you see these colors? They represent the concentration of surfactant chemicals on the surface of the bubble, and we also include the effect of the surfactant chemicals, which are basically a scalar, coming from the volume onto the surface of the bubble when the concentration in the volume is greater than the surface, or from the surface of the bubble into the volume when there is too high a concentration at the bubble. Okay? Further to that, we also have the effect of the surfactants being moved along the surface because of the tangential velocity field, and that you can see in the colors of the surface which show you the surfactant chemicals. Okay, so here in the beginning everything gets swept down. The bottom of the bubble has got a different shape because of the higher concentration of surfactants, and then the bubble does its usual dance. Okay. Let us summarize this a little. When you talk about multi-phase flow modeling, you need to know a little bit more about the kind of multi-phase flow problem that you're going to have. Okay? There are two basic approaches. One is Euler approach, where you assume that both phases are present everywhere, okay? And that the volume fraction is relatively high. The second approach is the Euler-Lagrange approach, where you will say that there is one dominant phase that we will represent as a continuum, and one dispersed phase, which will be represented as Lagrangian particles running through that continuum and exchanging mass, momentum, and energy with it. And those two sets of solvers are particularly well established. Okay? They've been around for almost 20 years. No, in fact, they've been around for more than 20 years now. Implementations in OpenFOAM have been documented in a bunch of PhD theses, validation papers, journal papers, blah, blah, blah. Okay? If the simple model of a monodispersed Eulerian system is not enough for you, you need to introduce a representation of droplet size distribution. Okay? For that, you can either use a method of classes or statistical methods such as QMOM and DQMOM, but this is built up on the basic Eulerian approach. For Lagrangian approach, there is a lot of submodels which need to be included together with the basic Euler-Lagrange principle, and you have to review which of these models are effective or valid for the problem that you're solving. Okay? The original implementation has been targeted on diesel combustion in internal combustion engines. You can stretch it to gas turbine combustion by changing constants, but if you try and do something completely different in chemical engineering, a full review is required. A special case of the solver is the free surface volume of fluid solver, which does volumetric surface capturing. Here we assume that between the phases there is a discrete interface, and that the interface needs to remain sharp, which allows us to collapse multiple momentum equations into a single momentum equation and add the terms into the volume fraction equation, which makes the interface pretty sharp. Okay? And further to that, there are additional solvers like the free surface tracking solver or liquid film model for wetted surfaces. Okay? Now, one of the models that's interesting for me is this free surface VOF solver. So I'm going to show you some of the things that we do with it in the naval hydro pack in the next few minutes. So in this set of slides, I will quickly show you some of the examples of what we do with the VOF solver for naval hydrodynamics. Okay, so the idea of the solver is that you no longer do just little jets or little vessels that are moving around, but we concentrate on the problems in naval hydrodynamics, and the solver has been significantly rewritten to be able to deal with very rapid simulation and high current number. Okay, so the first kind of simulation will be a weir flow, where you have a top lake up here, and then you let the flow go around the weir, looking at what happens in this region here and how wet does it get this region under the bridge. Okay. The problem with this simulation is that you have quite a lot of flow. Maximum velocity is of the order of 20 meters per second, and the original solver had current number limitations which made it run very slow. Okay, so this is, I think, about 5-6 million cell mesh, and the first time we ran it, it took almost 4 weeks on the supercomputer, and we had to speed this up. With the naval hydrodynamic solver configuration, we can now do it in a day. Okay. The reason why we could do that is that we have reformulated the numerics in the VOF equation and the pressure velocity coupling to deal with that sort of simulation. Okay. The second example that I have is something that I will ask you to model for me soon. And the idea is that we will take a two-dimensional dam break simulation and make it into a 3D with an original amount of liquid hitting an obstacle and flowing over to the other side. Oops. Okay, so for this kind of simulation, conventional solver will be good enough, so there will be no problem trying to do it. But it will also show us a few things, for example, how to initialize a non-uniform field, etc. The simulation where the naval hydropack is really good are the simulation of the following type. Okay, so if you have a ship, and then you're looking at the development of the free surface until you get steady resistance. Okay, this is about 5 million cells, and you can see how quickly you can develop the wave pattern on this. Okay, so the good thing about these simulations is that they're very, very fast. So for example, for a simulation of about 1.6 million cells, we can do it in 50 minutes on the workstation, which is much faster than other commercial CFD codes. The interesting part of the story comes when you start introducing waves into the system. Okay, so maybe first a little simulation to show you how the dynamic mesh part works here. The simulation is basically an obstacle at time 0. It is touching the free surface, and now we are integrating the 6 degree of freedom motion equation, which will let the obstacle heave and roll to find out how far we can get. More realistic simulations of this type will take something like a ship, which is released in a 6 degree of freedom way, and there are incoming and outgoing waves on that ship, and now you're solving not only the free surface but also the 6 degree of freedom motion of this ship. And eventually that gets fancier and fancier until we get to the point of, for example, an extreme wave hitting the top of the ship. And now you will see the ship trying to roll and heave in response to this wave. Okay, so the fancy things here is first a generation of an irregular sea state based on a non-uniform spectrum, and then coupling the CFD simulation to that wave that has been generated using potential flow tools in order to capture what's happening with it. Okay, so much for the moment. Any questions? In that case, let's have a 5-minute break, and we will do a dam break tutorial together. Have you done that tutorial already? Okay, I need to go through some of the aspects of it just to show you what's going on, but let me have a glass of water first.
Yeah,